morning all. How are you? Welcome to my channel Vijay Physics Prints. So last class we covered the electric field intensity at any point due to electric dipole, right? An axial line, what is electric field intensity at equatorial line, and instead of these axial and equatorial at any point on plane of the equatorial electric dipole, so there we calculated electric field intensity. Now today we'll discuss about two more concepts, right? The motion of charge in electric field. Motion of charge in uniform electric field. The electric field it is uniform. Uniform electric field. Uniform electric field means at any point in a given field, the field intensity has same magnitude, equal magnitude in same direction. That is known as uniform electric field. So the direction and the magnitude of electric field intensity, it is same at all the points in a given region, and the intensity, the field, it is known as uniform electric field. So in the uniform electric field, now we are placing a charge. This is the electric field intensity direction. The field intensity E bar in this direction. Now we are placing a charge Q in the direction of electric field. In the direction of electric field, the same direction in the direction of electric field. So initial velocity of the charge U is 0 starting from rest, accelerated in uniform electric field. Then what is the force acting on the charge? What is the acceleration? What is the momentum? What is the kinetic energy of the charge? Now we are going to calculate. So starting from rest, nothing but U equal to 0 in the direction of electric field, right? Then what happens? I'm calculating what is the force acting on the charge. Force F is equals to EQ, electric field intensity, into charge. The force acting on the charge due to the electric field, right? And second, acceleration. Acceleration F can be written as MA, which is equals to EQ. Then acceleration becomes EQ by M. This is the acceleration. Now velocity. What is the final velocity? Starting from rest. So U is 0. U is 0. Acceleration is EQ by M into T. So this is the velocity, final velocity of the charge in the uniform electric field. Next, what is the momentum? Momentum, linear momentum is nothing but mass into velocity. So mass of the charge is M. Velocity, just now we calculated, EQ by M into T. Of course, M is going to be cancelled out. Then momentum becomes EQ T. This is the momentum. Next, what is the kinetic energy of the charge? Kinetic energy is half mv square or p square by 2m, right? So then p square, nothing but E square Q square T square by 2m. This is the kinetic energy of the charge. And how much of distance traveled in the uniform electric field? How much of distance traveled by this charge? So the distance S is equal to ut plus of AT square. S is a distance, U is 0 of acceleration, that is EQ by M into T square. So this is the distance traveled by the charge. So the force acting on the charge F is equals to EQ. Acceleration EQ by M. This is acceleration of the charge. Final velocity, momentum, kinetic energy, and this is the distance traveled by the charge in the uniform electric field when the charge it is in the direction of the electric field. Okay. So this is in the direction of electric field. This is a case 1. Now the same charge perpendicular to electric field, what happens? Same direction, we calculated force, acceleration, everything. Now the charge it is placed perpendicular to electric field is a positive plate and this is negative plate. We know that the direction of electric field positive to negative, the direction of electric field intensity. Now the charge Q is placed in electric field with velocity U. Okay, so starting from rest. Okay, so the horizontal velocity it is taken as U. Consider the charge it is positive charge. Then what happens? The positive charge it is deflected towards negative plate. So it is just like a projectile motion, that will be horizontal projectile, right? So the distance covered in horizontal direction is x and in vertical direction it is taken as y. Just like a horizontal projectile motion. So what is the horizontal distance? Horizontal distance. X is equals to ut because horizontal velocity is u and acceleration, horizontal acceleration is equals to 0, is a uniform electric field. So at any point the force it is same, F is equals to EQ, right? So no change in velocity, therefore horizontal velocity is no change, therefore AX is equals to 0. Now what is the vertical distance? Vertical distance, nothing but y is equals to of AT square, ut plus of AT square, but the vertical component of velocity is 0, therefore the distance becomes y is equals to of AT square. But what is t here? I am writing t from this x by u, so therefore substituting y is equals to of a into t is nothing but x by u whole square. So this is the vertical distance traveled by the charge when it is perpendicular to the external uniform electric field, right? So far we discussed a point charge placed in external electric field, then what is the force, what is acceleration, and that with the charge it is in the direction of electric field and perpendicular to electric field. Now instead of a point charge, now we are placing electric dipole, then how it is behaves. So when the electric dipole placed in uniform electric field, what happens now we are going to discuss. So this is the direction of external electric field, uniform electric field, E bar. Okay, just imagine this is the dipole, okay, the dipole, positive charge as well as negative charge placed in uniform electric field. This is positive and this is negative. The distance between the dipole equals to 2a. So due to the external electric field, the force acting on the positive charge F is equals to plus EQ. Force on minus Q, F is equals to minus EQ. Equal forces but opposite direction, so that on the dipole torque is going to be developed. What do you mean by the torque? Torque it is nothing but turning effect. When two equal and opposite force acting on different points, the body is going to be rotate or turn. The effect it is called as torque. So two equal and opposite force acting on dipole, so that the dipole is going to be rotated like this. So this is positive, now it is negative. The distance which is equals to 2a. Okay, now this is the perpendicular distance. Perpendicular distance. What is the formula for torque? Torque is equals to R bar cross F bar. R bar is a perpendicular distance. Force, just now we calculated, F is equals to EQ. Now what is the R? Using this triangle, theta is electric field intensity, angle with electric field intensity. From this triangle, writing the value of sin theta equal to opposite, nothing but R, by hypotenuse, which is equals to 2a. So R equal to 2a sin theta. Now substituting torque, torque tau equal to R, which is equals to 2a sin theta, force F is equals to EQ. But already we know tau equal to 2aq. 2aq indicates dipole moment vector, electric dipole moment vector p bar. So the direction of electric dipole moment vector always from minus q to plus q. Remember, the direction of dipole moment is always from minus charge to plus charge, minus q to plus q. So here 2aq is replaced with p and E sin theta. This is the torque acting on the electric dipole due to the external electric field. This is actual initial place of dipole. But when I equal and dipole force acting on dipole, the dipole is going to be rotated, turned like this. So torque developed on the dipole. What is the amount of torque? Tau is equals to P sin theta. In vector representation, tau bar equal to P bar cross E bar is a vector representation of torque. Okay, remember this formula, torque P sin theta, and theta equals 0 in the direction of electric field. Theta is 90 perpendicular to electric field, and you can take theta at any values, 45, 30, 60, right, 60 like that. So different angles, different torque acts on an electric dipole. Any doubts? No. See, we discussed about torque. This is the initial position when torque acts deflected like this. When come back to the original position, restore torque. Restoring torque is developed. Restoring torque is developed on electric dipole. What is the restoring torque? That is equals to I alpha. Restoring torque. What is I? I is a moment of inertia. Moment of inertia. And alpha is the angular acceleration. What is angular acceleration? D square theta by dt square. The second order differentiation of angular displacement. So restoring torque, tau equal to I alpha. Torque on electric dipole, tau equal to P sin theta. When this torque and restoring torque equal, then the electric dipole said to be at equilibrium position. At equilibrium position, the torque is same as restoring torque. At equilibrium position, torque acting on dipole, which is equals to restoring torque. What is a torque? Just now we did have Pe sin theta. Okay, and restoring torque, which is equals to I alpha. Equal and opposite, the torque equal and opposite, nothing but minus alpha. So bring this side, that is Pe sin theta plus I alpha equal to 0. For small angles, in SHM, for small angles, sin theta is replaced with theta for small angles. Then what happens here? Pe theta plus I alpha is replaced with d square theta by dt square equal to 0. Simply I am rearranging like this, rewriting d square theta plus dt square and Pe theta equal to 0. Now if we compare this equation with SHM, what is SHM equation represents? Okay, little bit change. I is dividing. Okay, I am writing here this SHM equation. D square theta by dt square omega square theta equal to 0. I am comparing with SHM equation. So the equation is becomes like this: Pe by I into theta equal to 0. Now compare with SHM equation. D square theta by dt square, it is okay, fine. Theta angle is okay, fine. In a place of omega square. So what is in omega square? In a place of omega square becomes omega square, if we compare P by I. Okay, so omega equal to root over Pe by I. Omega is angular velocity of electric dipole. Now omega written as 2 pi by t. T is a time period. Root over Pe by I. Then time period becomes t equal to 2 pi root over I by Pe. This is the electric dipole time period in external uniform electric field. T equal to 2 pi root over I by Pe. I is a moment of inertia, P is a dipole moment vector, and E is electric field intensity. So the time period depends upon these three factors. So when we are placing dipole in a uniform field, it experiences torque, tau equal to P sin theta. To regain original position, restoring torque is developed. At the equilibrium position, torque which is same as restoring and in opposite direction. Therefore, we are getting the time period of the electric dipole which is equals to T equal to 2 pi root over I by Pe. Okay. So if you have any doubts, so make a question in comment box. Okay. So thank you. Like, share, subscribe my channel. Have a great day. Bye.